From the Library of Congress in Washington, D.C.
Good morning again. Buenos dias. My name is Stephanie Marcus, and I'm a research specialist in the Science, Technology, and Business Division. This is the first lecture of 2016, and it's the first in our 10th year of our collaboration with NASA Goddard. So it's been very fruitful, and we were trying to choose talks for this year, and there were so many good topics. Normally we choose 6, but we couldn't resist, and we chose 8. So it's going to be a very busy year. The next ones aren't till May, so we have a little time to prepare. And since we had a snafu today getting our speaker into the parking lot, we have plenty of time to get the next one, his parking. Today, our program is on El Nino, as you know, and our speaker is Stephen Pawson from NASA Goddard. He came there in 1997 as a meteorologist, atmospheric physicist, and he's been the chief of the Global Modeling and Assimilation Office since 2014 and has been on its staff since 2003. And if it's wrong, I got this off the website. So this man has a little bit different background from our other speakers. He was educated in England, pretty much, and I think you are.
I'm English.
British born.
British.
Yes. Let's see. He spent almost a decade at the Meteorological Institute of the Free University of Berlin, and he was also teaching there for 6 years. He was the editor for several years of the Journal of Geophysical Research, Atmospheres, which is published by the American Geophysical Union. He has a master's in atmospheric sciences from Imperial College, the University of London, and a PhD in meteorology from the University of Edinburgh. He was a postdoc in space and atmospheric physics at the University of Oxford. So, he's well educated. And since we all think we know a little bit about El Nino, we're going to listen to a man who knows everything about El Nino. Welcome, Dr. Pawson.
Thank you. Yeah. Well, thank you for the nice introduction. I thought I was going to tell you everything about El Nino today, and when I first started planning this presentation, I was thinking I was going to show satellite observations of like drought in Ethiopia, how the monsoon spun down in India, fires in South America, flooding everywhere. And when it comes down to it, there's just so much to say about El Nino. I actually ended up dropping a lot of those aspects from the presentation. I wanted to try to give just a zoom in on the Pacific Ocean where El Nino is really happening, and then a look at some of the things that are happening around the world because of that. But really, I want to try to give you a sense of a little bit of how El Nino works, what it really is, and also how NASA has so many satellite observations that can contribute to our understanding of the phenomenon, and also how we can use those with numerical models to do predictions of how things are going to evolve in the future. And in doing this, I want to try to give you the hint that NASA and NOAA play, in some ways similar, but actually very different roles. And that NOAA is an operational agency, and they have a fleet of operational satellites which they can use and do long-term products. NASA comes at it more from the space science point of view. We're doing research type of instruments, so maybe some of them are a little short-lived, but they set up standards that and demonstrate that observations can be made of different processes and that they can be used into the future. And that either gives NASA an incentive to continue the time series of observations, or it gives us a means of convincing NOAA to try to take on that type of observing. And what I want to try to do today then is just give you a flavor of how we work in that regard, of how NASA makes sort of almost revolutionary observations at certain times, and how we can use those to help put together the big picture of the processes at work. And I've tried to put a little history in as well, to try to show us how those people from like a century ago were able to just take a few points of information spread over time and put those all together and actually understand pretty much what we still understand today. It's just that now we have a lot more detail from the number of observations we have. This is a slide I started collecting things from newspapers. Yeah, I'm actually seeing a little problem here. And there's a lot of over the world, different newspapers are publishing stories about El Niño's back and showing droughts in Australia. There's flooding in Southern California. A lot of El Niño-related damage in the Philippines and Indonesia and things like that. There's been a lot of headline news about El Niño, and also, has it been affecting breaking the drought in California? Has it been affecting these big storms that came up the east coast of the U.S. and things like that? They're all phenomena that make the news and get into the newspapers. So my Verview, which has an O at the front of it usually, is basically going to say, what is El Niño? I'd like to try to give an overview of what it looks like. I've set the format of these slides. They're on a stretched screen, and it's kind of truncated on the 4x3, I think. El Niño in history, so a look at the historical observations, and then moving into NASA's observations before we go to the work that we actually do in the Global Modeling and Assimilation Office, which is using those observations alongside computer models, high-end computer models, to make detailed analyses of the three-dimensional structure of El Niño and forecasts of how it's going to behave over the next few months. And then looking at the view from space of different parts of the climate system that are affected by El Niño, and a little bit of a summary at the end. So start off with a basic description of El Niño. What is El Niño? And basically looking at the oceans and the signals that El Niño has. So I'm going to start with a map of global sea surface temperature. So this is what's called a Robinson projection. So it goes in a bit at the poles, and it gives you roughly the sense that the tropics are very large. And if we look at this map, this doesn't seem to be working. That one, the red one, that helps, yeah. Okay, so there we go. So this is sea surface temperature, and it's basically the Reynolds sea surface temperature time series is a very famous product. It's developed at NOAA, and it's used to produce essentially global maps at least every month of the temperatures of the surface of the ocean. And you can see what you expect at the poles, where there's less sunlight. It gets cooled much more. It's cold, so those temperatures are blue. They're just in the low few Celsius, and that down there. But by the time you get to the tropics, you can see the temperatures are well into the 20s Celsius, much warmer water. And in particular, what we'd like to look at today is this region of the Pacific Ocean, and we can see that over by Indonesia, and the maritime continent north of Australia, in the Western Pacific, the temperatures really are up to about above 28 Celsius. And that's kind of a magic number, because 28 Celsius is about the temperature that we need to have for deep, powerful convection to happen. So basically, over that region, we're going to get strong clouds forming, very deep clouds and storms. And in the normal case, there's a lot of precipitation in this region. And we can see what's called the intertropical convergence zone, which is essentially a warm tongue extending over to the East Pacific. That hits Central America. And if we look right on the equator, we can see cooler waters here off the coast of Peru. And that is associated with the currents. We'll talk about that in a few moments. But this is the basic structure of temperature over the Pacific Ocean. Warm on the west and cooler on the east, at least in the southern hemisphere and at the equator itself. And there's that gradient, and that's essentially the normal state of the circulation over there. This is basically pointing out what I've just said. And this black rectangle is essentially showing us the main region of interest for El Niño. So when you think about it, it's the tropical Pacific Ocean. But this map projection does a fairly good job at preserving areas. This is actually, it's about between 30 north and 30 south is half of the globe in terms of surface area. And this is almost half of that in terms of the longitudinal extent. So El Niño is a huge thing. It's affecting, variations in El Niño are really affecting the global temperatures because it's such a large area of the globe that we're looking at. What we tend to show when we're looking at El Nino and other phenomena is the anomaly. And that's the departure from the long-term average in this sense. So we look at an average from something like 1980 to 2000, and we do that and we subtract that from the actual year that we're looking at. And that's essentially telling us how different is this year from a normal year, if a normal year exists. And this is December of 2013 again, the month that we just saw. And we can see that in this tropical region here, there are really very small differences from that, from the normal situation. Yeah? So this is what we call a neutral year. There is no El Nino and there is no La Nina. Yeah, we're not going to talk too much about La Nina today. La Nina is essentially just an intensification of the normal state. So La Nina, where it's cold over here in average, it's just a little bit colder than normal in average, and probably a little bit warmer over here. The more interesting one is the El Nino, and this is the plot from the previous December 2015, the one that just passed. And here we can see a very different situation. Now we've got a slightly cool anomaly over the Western Pacific, but here over the Eastern Pacific we can see a very, very large red-colored contour that's showing us temperatures are more than 2 degrees above the typical situation. And this is the development of the El Nino case, where the warmth has basically moved across the Pacific to the other side. And now south of the equator around Peru, there's warm ocean temperatures there. And that's showing up as that anomaly. There are other features you can see too in the other oceans, but they're less of a concern today. Except one thing here. I'm just going to toggle back to the 2013 case. Already, we're seeing this very warm anomaly in the Pacific Ocean off the west coast of the U.S., and that's been referred to quite a bit in the press as the blob and things like that. It's basically a warm anomaly off the coast of California and the entire west coast here, and this is probably related to the drought that we've been experiencing in California and on the west coast over the past few years. This has been quite persistent, and it's led to the anomalously low rainfalls over the west coast, the setup of the drought and things. Or if it hasn't led to it, it's associated with it. It's all part of the same sort of large-scale pattern of variations in the atmosphere. And you can see when we go back to 2015, that's still apparent up there as well. And that's probably going to be important just towards the end of the presentation when we talk a little about California. So that's essentially what I wanted to show at the beginning. Now, just one more thing. If we look at this map here, we can see that this is directly compiled from observations. So observations are coming in from ships, they're coming in from satellite observations of the ocean temperatures, and from satellites especially, they're very spotty because there are a lot of clouds in the way and things like that. So you can see that spottiness come through on these maps. Yeah, especially outside the tropics, it's got a bit of a spotty structure. Whereas on this plot, this is essentially the same field. It's using the same observations, more or less, with a few extra ones added. This is what happens when we actually assimilate those same observations. And essentially, assimilation is the art of, or the mathematics really, of putting together observations into a very complex computer model. And we're essentially, if you interpolate, you'd have information about this point here and this point here, and you could draw a straight line between them and come up with some values from in between. What assimilation is essentially doing is a very sophisticated interpolation, in that the model that we're using to build that structure in between the observation points is based on the dynamical equations of motion. So we're actually using that to move water masses around when we do it for the ocean, and that gives us a good estimate of the state of the ocean based on the observations in other places. So it's essentially a very expensive three-dimensional interpolation that we're doing to come up with optimized analyses of the entire globe, and we'll see later we get the three-dimensional structure of the oceans as well from just a few bits of information about the vertical profiles in the ocean. And the point here being, if we toggle back and forth for a moment, here it's very noisy from the pure observations. Here we get a much smoother and much more sort of realistic, dynamical-looking field that's taking into account the motions of the ocean currents and the surface winds blowing over it that help define these fields. So that's essentially the work that the Global Modeling and Assimilation Office is involved with in this. And here again is part of what we do. this is showing us sections across the equator from the Indonesian side of the Pacific to the South American side of the Pacific, and it's showing depth in the ocean from 0 to about 300 meters below the surface. And this is the temperature anomaly as a function of depth of the ocean for December of 2013, where we see just a very weak 1 or 2 degree region that's 1 or 2 degrees warmer than normal. And for December of 2015, the strong El Nino year that we just saw at the top. And here you can see that this temperature anomaly that we were looking at the surface just a moment ago is really, really prevalent below the surface, and it reaches about 7 degrees Celsius over this side, this South American side of the Pacific, so under the ocean surface. Now, as I said, this analysis is made using the surface ocean observations. It's made using an analysis of the atmospheric state, so we know the winds in some detail. And it's also made using just very, very few profiles of the ocean temperature and salinity structures from some buoys that are moored over in the Pacific at certain locations. But really, it's just a handful of information that's actually measured about that. And we're using the model to fill in the gaps and come up with a three-dimensional picture. The other thing that we sometimes use, and I actually believe it's actually not in this run, but we sometimes use measurements of the sea surface height that we make from space, and we'll be looking at those in a while. And essentially, that's useful because we obviously from space you can't see below the surface of the ocean in most cases. It's basically optically thick, so all you can do is measure the top. Temperature is one thing you can measure at the surface. If you can measure the height of the ocean, you're essentially saying, if that water in there is warm, it's going to have a larger volume, so it's going to push the height up. So these sea surface height observations are telling us about the temperature of the water over a huge deep layer beneath the surface. And so that's the type of thing that can go into getting this analysis as well. And so moving away from that and going back to the kind of the schematic, and it's always tempting to try to draw nice schematics of what's happening. And actually, these days, if you look around the web, you really find some fantastic ones. And this one, I think, sums up what's happening and what we've just talked about. It's essentially showing the ocean surface, showing the normal warm temperatures over to the western part of the Pacific, and then the deep convection above that, and this circulation in the atmosphere that goes up in that region, and it goes across and down, and then the trade winds, they're called, running across the ocean surface up there. And that's called the trade winds because of the ancient shipping routes that the sailors used to make use of those to get across the Pacific. Essentially, they'd be blown across there. And it's showing underneath the ocean surface, it's showing the thermocline. The thermocline is essentially the boundary of the water that's mixed up by turbulence caused by wind stirring it, and the deep ocean waters, which are not affected by the surface winds so much. And so what we're seeing is that the thermocline is quite far below the surface on the Indonesian side, but then on the Peruvian side here, there's basically upwelling. We'll talk about that again in a moment, and that's pushing the cold, nutrient-rich water from the ocean, from the deep ocean upwards on the coast. And so the layer that's actually affected directly by the atmosphere is very thin at that edge of the ocean. So that's the normal state. And then if we look at the El Nino state, we can see the warmer temperatures moving across the equator. The thermocline tips, so we don't get so much of the upwelling over the eastern side of the Pacific. And the deep convection in the atmosphere moves over to the central Pacific and also a little bit more over to the South American part of the atmosphere. And as I said earlier, the La Nina case, which is the opposite of El Nino, is basically an intensification of this state. Typically, the thermocline may even meet the surface just off the coast. So it's just an intensification of how cold it is over that side of the Pacific and a little bit warmer over the other side. And I've tried to give a citation to most of the figures I do use from the web, although this is I think that's the original site. This is these images float around all over the place, so it's hard to know exactly who did that one first. So just looking at this, the Pacific then, essentially in normal years in the central Pacific region, we've got sort of moderately warm temperatures. In the El Nino years, it gets much warmer. And this is then used as a metric of how strong the ENSO events are, the El Nino events are. these four regions, Niños 1, 2, 3, and 4, the red shaded regions, were typically early locations used to define the strength of the El Nino events. And the reason they're called 1, 2, 3, and 4, I think, is because these are places where the ships used to sail. And so they actually made measurements using, they threw a bucket over the side, pulled the water up, and put a thermometer in it, basically. And they get measurements of the ocean surface temperature. And that's still done today by research vessels. And so these were four regions where ships sailed, and it's obviously to do with trade between the ports of South America here and the Asian ports on these links. What we typically use these days to define the El Nino is this region we call Niño 3.4, which has got a little bit of 4 in it and a little bit of 3. And I think people converged on that just because it really shows a decent signal that we can relate to what we regard as ENSO. And then if we look at this, the time series of the Niño 3.4 region, this is essentially showing us how things change over the years. This one begins in 1950, and it goes up to actually the present, to about February of 2016. This is, again, it's compiled by NOAA, NESDIS, one of the labs out in College Park. And essentially, you can see these very cold years. Basically, if it gets a half a degree cooler than normal, that's termed a La Nina, at least if it persists for 3 months. And if it gets half a degree warmer than normal and persists for 3 months, then it's regarded as a El Nino. And of great interest are these three big El Nino events in 1982, 83, 97, 98, and then this present year. And you can see that at least over the last 50 years, these three events stand out. This one was quite widely studied, and it's a very interesting one in many ways because it actually coincides with a major volcanic eruption as well, El Chichon. So it's actually hard to use that to decide what the climate anomalies are associated with El Nino, because there are also big climate anomalies associated with all the volcanic sulfates and that got into the high atmosphere. So that one's less useful, at least less useful in terms of defining climate anomalies. But as we get through to 1997, 98, we're getting to the point where we have a fairly clean atmosphere, so we can look at the climate anomalies. And the other great thing is this is around the time when NASA did start having some research satellites available. And in particular, the TRIM mission that measured global precipitation had just been launched when this event started. And we also had some measurements of the color of the ocean, which tells us about how many phytoplankton are in there and things like that. This starts to be an interesting one for NASA. And then, of course, the present one is as strong as, by this measure, that one, in some measures it's a little stronger, in other measures it's not quite so strong. So this, again, is giving us an opportunity to look at El Nino with a very modern fleet of satellite instruments alongside everything else that we have. And I think just basically the forecasts of this extremely strong El Nino that started coming out towards the middle of last year were really alarming because people remembered what happened with the 1997-98 one. That was a big global scale climate response. It starts with that warm water by Peru, really leads to a lot of anomalous rainfall in Peru. A lot of rainfall in a mountainous terrain like that leads to catastrophic landslides. So a lot of environmental damage, which is by both flooding and landslides. So there was a lot of concern about that happening this year as well. And I was going to show a bit more about that, but I didn't in the end. So I'll say now, that actually, I mean, even though there was some strong rainfall in Peru, it didn't turn out to be quite as bad, because if we look at these anomalies, the Niño 1 and Niño 2 are basically telling us about the temperatures just by Peru. They were not quite so strong this year as they were in 1997, 98. So essentially there's been a tendency for the El Niños to be peaking in more of the central Pacific rather than right on the eastern Pacific over recent years. And this, even though this one was really big and bigger in some ways than 97, 98, its horizontal extent wasn't quite as large, so it didn't have such a big signature down here. That means that any weather systems that are moving into Peru just don't get quite as much energy from the oceans beneath them as they go in. A little less water because it's not quite so warm, and so the rain has probably not been quite as bad as it was in 97, 98. That's not to say that there hasn't been any severe storms in Peru, but that it probably wasn't as bad as they were dreading at the beginning of this. So with that, I've tried to give a sort of an overview of the basic characteristics of El Nino and what it looks like. I wanted to just briefly go through a little bit about the historical role of El Nino. And it seemed good to start with an old map of Peru. So that's the Peruvian coast, and you can see that north is pointing that way. So orientate yourself. And this is actually this map was actually drawn up by Mercator and one of his colleagues. And there's actually a Mercator map projection that's very widely used to this day. It's essentially a regular latitude longitude grid. You really. I just always find it very impressive. These people would, they'd be out on ships and making measurements, and they get some fairly accurate maps of the coast. They even put ships out in the sea and things like that. And sometimes you find monsters. I don't know about these ones, but so this is a nice one. And you can see on this too that they've really made effort to show the very tall mountains, the Andes, very close to the coast in Peru, which rise really dramatically up there. So. That's an old map that's found, and this is a map of basically the ocean circulation off South America. Again, a pretty old map. This is the coast of South America, and essentially there's the Humboldt Current runs up the coast in the ocean, and as we get to close to the equator, that starts to be pushed offshore by the winds flowing off the continent. Also, the Earth rotation kind of encourages that to flip away. So as we get to Peru and Ecuador, that current is moving away from the coast, and that's essentially dragging this water up from below. So that deep water from the deep cold ocean is going to get drawn up from the ocean from the deep ocean, and that comes up just around here. And as the settlers in the 17th century and way back started moving into Peru, they basically started discovering that there was a lot of fishing, especially anchovies, off the coast. And essentially what's happening there is that this cooler water that's upwelling from the ocean floor is bringing up iron and other nutrients. And that encourages the growth of phytoplankton in that water. It's got plenty of light to grow as well, so it's really the ideal conditions. And these anchovy fisheries are essentially still one of the biggest fish sources for the entire world. But what actually happened is that the old fishermen noticed that every few years the fish would go away. And this is basically the ocean warms. This is the El Niños coming in. The ocean warms. That upwelling of the deep cold waters to the surface is cut off. The phytoplankton move. They're upwelling somewhere else. So the fish go away and feed elsewhere. So essentially, there's a dramatic decline in the fisheries in those years when there's an El Niño. And the name El Niño actually comes. It was given to it by the Spanish settlers in Peru and Ecuador. Essentially, this was happening around the end of the year, around Christmas time, and they used to call this the boy child, or El Niño. And that's where the name comes from. And then the La Niña, I think, the name came some years later, because it wasn't so dramatic, because you still get the fish in a La Niña. So for those people, it wasn't so critical. And so that's loosely how things are working around the coast of South America. And just flipping onto a very modern view, this is a NASA view. This is actually from the SeaWift satellite, which was observing around 1997 and 1998 after it was first launched. So SeaWift measures the color of the ocean essentially at different wavelengths. And now the color of the ocean, if it's very green, it means there's a lot of phytoplankton in there. If it's very blue, it means it's very clean, so there's no life. So you can infer from this the amount of phytoplankton in the ocean, and you can then infer where the fish may be and things like that. But these plots are essentially showing that in December of 1997, an El Nino year, we have to look at the scale a bit carefully here. This is a logarithmic scale, so this dark blue has 10 times less chlorophyll than this sort of pale blue, and by the time you get to white, that's 100 times less. So between there and there, there's about 100 times less chlorophyll here than there is there, basically. This is the El Nino year. You're seeing, not particularly much, but compare that to December 1998, a year later. So 97 was the first year of measurements from SeaWift's. 98, you're seeing very white regions there. So you're like in the few the few milligrams per cubic meter of chlorophyll in those regions. So we're essentially able to show, using space-based measurements, the thing that the Peruvian fishermen knew all those years ago, that the phytoplankton had gone away in the El Nino event, and there they are in the La Nina in this case. So you can actually see this from space. And these are really, we've now got a really long time series, about more than 20 years of measurements of ocean color, and there's a new mission we've just got funded at Goddard to take that way into the future. So we're able to do sort of climatological studies now of ocean color and infer phytoplankton changes over time. We have models that run and do sort of single, like diatom and multi-bodied phytoplankton that kind of change over time, and that's one of the great things that we actually do with our satellite observations. So going back to history, and we come to Sir Gilbert Walker, who was also English. He was a mathematician physicist, and essentially he was posted to India as the director of the meteorological observatories there. And he had he just heard about, there'd been, I'm sorry, I'm not saying this very well. In the late 19th century, there had been famines in India because the monsoons had collapsed. And Walker knew about other things. He knew about pressure measurements, surface pressure measurements over the Pacific Ocean. And he basically had an army of staff in India working on time series analysis, essentially. What we now do very routinely on the computer, he had people doing for him. And he was able to establish sort of relationships between different variables that were being measured in the atmosphere at that time. And it turns out that the circulation with the ascent over Indonesia and then the transport across the atmosphere and descent near South America, that's now called the Walker circulation, named after him. He's basically the person who put this all together. And what he actually defined was what's called the Southern Oscillation, which was a seesaw in surface pressure, again, in the surface pressure difference between Tahiti in the mid-Pacific and Darwin in Australia. So he was able to deduce that those things moved out of phase, and this is the change of mass of the atmosphere. He didn't realize at that point that was El Nino. It was Birkenes, I guess, in the 1950s or 60s, who put that all together and realized that essentially the southern oscillation in the atmospheric surface pressures is essentially the same signal as the El Nino event in the tropical Pacific Ocean. But coming at these things with just a few point measurements of meteorological conditions at the colonial sort of stations that they'd set up over time. So this is a much more modern map. It was in the 2007 IPCC report, and it's showing essentially this Darwin Southern Oscillation Index, the Tahiti-Darwin surface pressure change. And in this case, actually, we have to be a little careful. A positive value is actually a La Nina. A negative value is an El Nino. They're anti-correlated between the mid-Pacific surface temperature. But essentially what it's saying is that when we have a negative anomaly in this pressure difference is corresponding with this will be a positive anomaly in the surface air temperature. So the El Nino has warmer temperatures over the eastern Pacific, and that has that particular signal in the surface pressure difference. So you can see a signal here in the surface air temperature. In the surface pressure, this is essentially the Walker circulation. When it's going up there, the pressure's lower. Down here, the pressure's higher, and that seesaws. And the precipitation, essentially the clouds are moving over the mid-Pacific in the El Nino event. So in the El Nino, the precipitation is increased in the mid-Pacific and decreased over Indonesia. And that's the coherent dynamical framework. Walker put that together. We've got a lot more observations and a lot more time to have done that in the meantime, but that still holds in those things. So that's then showing essentially what people were able to do in historical times with very few observations. I now want to move a little into the time when we have NASA observations, and I want to emphasize the view from space, showing the advantages that a satellite can have over these in situ observations. We start off a little more with just repeating the map of where we're looking in the Niño 3.4 region. And this time I'm going to show the historical ship tracks as well. This is obviously not NASA observations. This is ship observations that were made, I think, towards the end of last century. And this is averaged over a long time, so there are a lot of tracks in there. And unfortunately, the Pacific on this is over here. But you can see that there's the coast of South America. You can see fairly dense networks of ships off Peru, and then crossing, in the trade winds, crossing the Pacific and coming into Asia. You can see, there's some very interesting things about this, because all the ships, if they wanted to go around here, they had to go all the way around the Cape, same going past Africa. So if we look then at a more modern ship map, we can see the Panama and Suez canals have opened up, and that has totally changed where the ships go. The distances are much shorter going through, so really very few ships now are going around these regions, but many more passing through the channels, through the Red Sea, through the Mediterranean, and then through the Panama Canal. But still, the point being, for both the historical time and the present time, yes, you do get quite a lot of information from ships, but it's very, very selective where you actually have that information. It's analogous really to the weather observations that we have. For the weather forecasts, essentially we have a lot of balloon observations over land. So North America, Europe, Asia is very dense in observations, but really very, very few of those over the oceans, because there's no one there to observe things. And similarly, in unpopulated land regions don't have many observations there either. So essentially, knowledge of surface temperature from ships is essentially only coming from where the ships sail. So what NASA does is basically provide a lot of different types of observations. I'm actually going to skip this slide, and I'm going to show this one. Maybe. And this is basically showing NASA has about 20 satellites in orbit right now. Most of them are polar orbiting, which means that they essentially just go round and round and round in a circle, and the Earth spins underneath them. And because the Earth turns once a day, we basically get a map of the entire globe from each satellite over each day when it's in a polar orbit. And this is the fleets. You can see some of them are chasing each other around. That's actually called the A-Train. And that's the name. Basically, they're all trying to measure essentially the same air masses, one after the other there, so and get information about different properties of it. One interesting one, and it's always the same with this movie, as soon as you want to start speaking about something, it disappears around the back. So there's the space station. Yeah, it's gone again. But a very different type of orbit is the International Space Station. Here it comes, like around there. So that's in a much different orbit. It's much more inclined. So it's essentially going around the Earth more frequently. And what that means is you actually, whereas these polar orbiters, you only see one time of morning and one time of night, the space station, you basically go through the whole day, and you can see things at all times of day. And that can be really useful information for things that vary strongly through the day, if you're able to see them from that orbit. A whole bunch of things like QuickScat you just saw go by. That's actually a radar, and it's measuring the roughness of the ocean surface. So you're able to get information about waves and things like that from that. It seems to have stopped. OCO2 down there is measuring carbon dioxide in the atmosphere. SMAP, which seems to have got distorted as well as stopped, is measuring soil moisture from space. That's a fairly new mission. And actually we had one called Aquarius up there. That failed, unfortunately, last August. And we're hoping we're going to be able to use the measurements from SMAP to replace Aquarius and get information about the surface salinity of the oceans, the saltiness of the oceans. And that's also a really important part of the circulation budget. Essentially, you've got cold, fresh water coming as ice melts in high latitudes. Colder water comes up. And then where it rains onto the ocean, that's diluting salt, so it's fresher there as well. So with things like that, we're able to put together a big picture of how precipitation's happening and how it's affecting the ocean, how if ice is melting in the polar regions, that's affecting the salinity of the oceans, and that's all what drives the large-scale ocean circulations that we have. I wanted to talk a little bit about the sea surface height. I alluded to that earlier. as I said, you basically can't measure temperature below the ocean surface from space. So, but what you can do is kind of infer that if it's warm, it's going to be higher. So essentially, this series of satellites, they're actually international partnerships with Europe, and they're led by the Jet Propulsion Laboratory in California. We've just launched Jason 3, which is the third one in the series of Jasons. Jason 2 was launched in 2008, Jason 1 in 2001, and before that we had Topex Poseidon, which was launched in 1992 and lasted through 2006. So we've got a long time series now of about 20 years of information about the height of the oceans. And this is as I said, it's sort of an integrated quantity of the vertical temperature profile. This is an example of, again, an anomaly map for February the 22nd of this year, so really quite recent. And it's showing us essentially the same thing that we've been looking at with the temperatures. Where it's warm, we've got a high anomaly in the ocean surface. So it's warm, it's thicker, it's raised up. And here over the eastern Pacific, it's lower than normal. So that's the signature of the El Nino in the ocean height. Now, how we measure that is actually very, very interesting. Essentially, the altitude of the spacecraft is measured very accurately in reference to a certain a geoid, it's called, a reference level. And then by beaming a radar down, it knows how much signal it's sent, and it times the time for it to come back, the signal to come back. And then it can calculate the path between the spacecraft and the height of the ocean. So with those two pieces of information about the height of the satellite above this reference level and the distance from the satellite to the ocean surface, which you can measure very precisely, it can actually measure the height of the ocean surface to within, I think it's about 3 centimeters. And from an orbit about, I think it's about 850 kilometers above the Earth, 500 miles up. So, that's the type of information we can get from space that we cannot get from down here. At best, you can't actually measure the height from down here because you'd be on a ship and you don't know how high you are to start with. So that's that. And another type of observation that we can make, this is actually rainfall. And again, it's comparing the rainfall measurements on the left for 2014, on the right for 2015, and it's 2 different months. I think it's September and October, September at the top, October at the bottom. And if you look at this carefully, you can see the differences with the El Nino states, and then when you look at it from here, you can't see any differences at all. So maybe we'll just skip over that one. There's definitely a signal of how it's actually difficult to get the reference. But I should stand near the microphone. Sorry. It's essentially, I think that's the equator, and this is closer to the equator there than. I'm sorry, this over this side in 2015 are closer to the equator than these ones. And you can see actually, it is more red over the mid-Pacific than it is here. So, there's if you know what you're looking for, then you can actually see the signal of El Nino in those observations. And those really are just 2 of the different types of observations that we have from NASA that help us put together a sort of a quantitative picture of what's really happening in the El Nino event. The ocean height that goes along with the sea surface temperature that we actually get from NOAA largely. And this, again, the Global Precipitation Mission. The TRIM was a predecessor of the Global Precipitation Mission. If you remember, that's the one that crashed into the Indian Ocean about a year ago. TRIM, it ran out of fuel, and then it was basically, they descend back through the atmosphere then. But now there's the Global Precipitation Mission up, which should give us information about rainfall and clouds for the next few years as well. So I wanted to give a brief look at our computer-based analysis and prediction. And I see I'm actually running out of time a little bit, so I have to be careful. But essentially, I already mentioned, we're taking a lot of these observations that are made from Earth and also combining those with observations from space and using advanced analysis techniques to come up with analyses of the 3-dimensional structure of the oceans as well as the atmosphere. And once we have a good estimate of the ocean state on any day, we can actually start to predict what it's going to look like in the future. So every month, we're running a suite of forecasts. It's called an ensemble. I think right now we run 17 members each month. Some of them start on different days, and some of them we tweak the actual state because there is some uncertainty in it. So we try to build up some suite of ensembles. And then we can make a forecast. And these are then the forecasts that we ran last August. We'd already, in about May, we'd been starting to see a signal of a very, very strong positive temperature anomaly in this Niño 3.4 region. And this is the ensemble. Often when you run an ensemble, this is the zero line, and you'll get a few going up there and a few going down there. And the average of them all is roughly what you put out as the best guess of where we're going to go. In this case, we'd already seen the observations of sea surface temperature were ramping up, so we were warm to start with, and we're predicting then a very warm anomaly. That's about 3.5 degrees on the average, but some of them were almost 5 degrees, and most of them were above 2.5 degrees. So we were predicting fairly early on a very strong El Nino for this year. And we were a bit worried about it because a lot of the other centers weren't predicting something quite that strong. But actually, it turned out as the year went by, the Australians put out a press release saying it's going to be the strongest El Nino ever. And it turned out that these 2 or 3 groups that were forecasting the very strong event were actually right. This is what's called the National Multi-Model Ensemble. This is a project organized by NOAA, and they gather this information from different centers that make the forecasts. And what I just showed you from our group was all of the different ensemble members. You can then make an average for each group, and this is the averages for each of a number of groups. We're on this, we're the yellow one. We are the strongest on there. One of the Canadian models is a little weaker, and the average is here. Most of the models were clustered just a little bit colder than the average of all of them, and that's just because you have 2 fairly high ones above it. So, there was a good consensus this year that there was going to be a very strong El Nino, and in the mid-Pacific, it really looked as though it was going to be the strongest one. This is a history map showing our forecasts that began in August of each year. So essentially, you're seeing this El Ninos and La Ninas going along. The blue line here is the observations, those Reynolds sea surface temperature observations, and here. So here you are in January and February, it's very warm, and here is our forecast. So we'd greatly overestimated the forecast in that previous event in 97, 98. But generally, we do a reasonably good job. We were a bit concerned about this one being so strong because on the basis of this one, we were thinking, well, okay, we're saying it's strong, but it's going to be down here. But actually, unfortunately, I couldn't find the plot that shows it, but we actually did a pretty good job. This was one of the strongest El Ninos ever in the mid-Pacific. So these forecasts of sea surface temperatures in that region were actually pretty accurate. And so what's going to happen now that we've gone through this time? We predicted a big El Nino. Now here are the forecasts that begin in January of 2016. You can see we're at the peak now, so we're up there somewhere at the 2.5, 3 degrees. As time goes by, we're predicting that to fall away and just get loosely negative. So essentially, the El Nino is dying out. Some of the groups are now predicting, a reasonably strong La Nina event is going to happen later this year. On the basis of this, we couldn't really say that our ensemble is doing that, but that's still a possibility. There's often a precedent that when you have a strong El Nino event one year, the following year you get a reasonably strong La Nina event afterwards. So it's like an over-recovery of the thing. So that's one of the uses of the analyses, making these forecasts. What I'd like to show now is another movie, and this is going to show us the sea surface temperatures throughout 2015, and this is the view from the top, essentially. So this is from our analyses, and it's showing, essentially how the warmth has built up and propagated across the ocean. This is made from daily or sub-daily data, so you can see a lot of movement. That's starting again, and now what's going to happen? It's going to tilt on its side in a moment, and you're going to start seeing this as a function of depth in the ocean. So there you go. So now you're not seeing just the surface, but you're seeing the situation under the ocean surface. And that's starting again now in January of 2015. And you can see how the anomalies are building up in the lower layers and then really moving over to the ocean surface as the event matures. So that's November. Here's now a very mature El Nino event, January, February, and stops. It's already dying off a little bit, yeah, you see, compared to January. So, we've peaked here, and that's dying out now. But this is, that's basically a summary diagram of what happened this year based on our best estimates using as many observations as we could use. Now, I'll just talk about the drought in California at this point. the view from space. So essentially, this is a NASA view of the drought in California. It's essentially looking at the vegetation derived from MODIS, which is an instrument on the EOS Aqua satellite. And essentially, anything brown means that there's way less vegetation there than there should be. And so compare this with maps of high temperatures. This essentially means, it's been hot, dry, the plants haven't survived. So we're on strong anomaly there, down, through much of the west coast, in the mountains and close to the coast as well. So when we heard about this big El Nino coming, there's been precedent in the past to say, okay, a large El Nino means a lot of rainfall in California. And so has there been rainfall in California? Well, here's another view. This is NASA's GPM satellite, and this is essentially going to build up, showing you the accumulated rainfall over each month for December, January, and February. And yes, you can see we got quite a lot of precipitation on the northern part of the west coast, but really not a huge lot over the Sierra Nevada and that in Southern California. We got plenty on the Gulf Coast, some storms, and you're going to see one event, the one that we got, the snowfall event, which was a typical East Coast storm. So on the basis of this, at least until mid-February, there had not been a huge lot of rain in California. And this is a map again from NOAA, sort of summarizing it's the average precipitation between over December, January, and February. And typically in a strong El Nino year, it's a little cooler down here, warmer up here, and blue here means wetter, so a lot more rain on the west coast, and actually typically across the Gulf Coast. It's kind of well known the Gulf of Mexico gets pretty wet in El Nino events. Also people thought, this year, 2015, 2016, not so much rain over in the Gulf, not particularly wet. Also, not a whole lot of rain in California. There's been a lot of rain in the Pacific Northwest, but really not so much in California. So really, we haven't had this massive deluge throughout the entire winter. I think since this map was made, there was actually some fairly severe rainfall just a couple of weeks ago, so that didn't make this map. But in general, this idea that a strong El Nino means a lot of rain throughout the winter in California is not holding up this year. Now, there's a couple of possible reasons for that. One of them might be that warm blob off the coast that's keeping things warm out there and directing the storm tracks slightly differently than normal. But more generally, I think our knowledge of El Ninos and their impacts on North American rainfall is actually based on very few events. And it may just be that every single one of them, just like the ENSOs themselves, each one is very different. Maybe the response in the higher latitudes is also affected by other factors, just the positions of the waves, which affect where the storm tracks go, and that. So I think it's not such a clear-cut thing that strong El Nino automatically means rain in California. And we know for a long time that a moderately sized El Nino, there's really no correlation between Northern Californian rainfall and the El Nino pattern. So we're probably just in the situation where we have so few large events that we don't know statistically what really happens. So the summary and outlook, I'm trying to keep this short. We do have a broad understanding of El Nino and its importance in climate variability. I've tried to give you a few examples today of, about the structure of El Nino itself and on the long-term effects. To do that thoroughly, you could have a lecture every week and for 3 months, and I think that would be too much. So I can encourage people to go away and take a look. The traditional viewpoint of the measurements from ships and from the ground is supplemented by NASA satellite observations, and essentially with that we're able to get global observations of many different quantities that we can put together using our complex data assimilation systems, and in that way we can build more complete pictures of the entire Earth system and how different processes start interacting. And that's one of the more, for me, that's the really interesting part about this right now. We've got essentially an unprecedented number of satellites flying, and we're able to see so many different parts of the Earth system now than we could a few years ago. That this is really a very exciting time to be working in this science. I've barely touched on the broad spectrum of NASA observations of the Earth system, but I hope I've given you some flavor of what we have. And despite all of this, I still think there are a number of points where our understanding isn't all there. So what we're really trying to do is bring together these satellite observations with the models so that we can improve the representation of processes and improve the fidelity of these predictions, not only of the 9-month seasonal forecasts, but also the IPCC models that do climate assessments. Some of those have a reasonably good El Nino representation. Some of them it's too weak, or some it's too strong. Some of them it hits the wrong periodicities and things. That got better between the 2007 and the 2013 climate reports, but they're still not there. So there's really a great hope that we can use our observations to improve these models and come up with a better prediction of climate and the role of El Nino in climate. And also, even the role of El Nino in a changing climate isn't well understood. We know surface temperatures are warming. We've had this general temperature increase. Even basic things now, like if we're looking at a 40-year time series, we can't assume that the average El Nino is not affected by climate change. We need to start thinking that the average it should be something that increases slowly with time. And then we might come up with a slightly different conclusions of how these things happen. So I think those are some of the things that I'm hoping we can use NASA satellite observations to address in the future. Just want to thank everyone here, as well as my colleagues, our funding and our computing center in particular. We keep them really busy with our things and end up with some contact information if anyone needs it. So I'd like to thank you very much for your attention, and thanks for coming.
Have had all your questions answered, but if there are a few more, we can take them. And when you ask a question, if you would repeat it so everybody.
Okay.
So it's on the recording.
On the recording, yes.
Yes.
Steve, what's your general thinking about as the climate gets warmer, ocean water gets warmer?
Yeah.
Does that make more El Niños or?
I mean, El Niños have been happening for as far back as we've had observations, and people have even gone back thousands of years and used records of sediments on the ocean floor. They've used tree rings, they've used many things, and you can reconstruct these climate fluctuations that are El Niño-like. So El Niño's been around for a long time. It's going to persist into the future, and the basic mechanism of El Niño, just a warm, taking that warm water from here and moving it over here, is probably not going to change. But the difference could be that if you're just in general, if you're a degree or two warmer, then the response is nonlinear. So triggering clouds is not, that could change, because even though you're colder than normal, you could still be above the temperature where you're triggering clouds if your climate has changed a lot. So, things could change in the responses, and I think, that's a very interesting type of question to be looking at.
You can choose.
Yeah, okay.
Well, with respect to sea surface height measurements,
Yes.
what does an accuracy of 3 centimeters mean when clearly the wave height is much larger than that?
That's right. So the question then about the accuracy of a 3 centimeter measurement of the sea surface height when waves are much larger. Waves are a separate thing. We can try to model waves separately from the actual mean height of the ocean that is being looked at. And so I think that if there's some element of time averaging, then the wave moves through and you get the average of what's there without the wave. So getting that reference height is very critical to this, and not measuring the crest of a wave. You're absolutely right. Yes.
So does the satellite have sufficient time resolution to be able to do that average over a wave?
Usually the satellites, you can do it in two ways. First of all, if the observation window is long enough, then the wave just moves through anyway. Or if you're not having the wave move through, then you basically aggregate over several measurements to get rid of the shorter scale signatures. That's a very normal way of dealing with fast changes in satellite observations.
I have a question.
Okay.
How does the satellite measure the salinity of the water?
That's measuring emissions of light at particular wavelengths, and that emission is affected by how much salt is in the water.
Okay. One more?
Yeah.
What's the Nino and the salinity of the ocean, if any?
Okay, so it's fairly complex. Essentially, the salinity of the tropical ocean is in part determined by rainfall. Through an El Nino event, the rain will move because it's raining where it's warmest over the ocean. So essentially, your fresh water, the non-salty water, is getting put into the ocean in different places. So that's probably the most basic aspect of the salinity that we can see.
Well, it's been very interesting, and I think the next party we can go to, we will be the center of attention with all our new knowledge. We want to thank you so much.
Okay, well, thank you too. Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.